Good afternoon, everyone. My name is Paolo Piccione. I am from the University of São Paulo, Brazil, and I'm a member of the IMU Executive Committee. So it is a pleasure to welcome you to this IMU Institute, Isaac Newton Institute Mathematical Colloquia and Panels, organized on the occasion of the IMU Executive Committee meeting here at the Institute. Thanks to the Institute, to the IMU, and to all of the participants for being here today. So, named after one of the most influential scientists in history of humanity, the Institute stands as a reminder that we are not in a random country, but rather in a land where science and math have flourished for centuries. So beyond the strictly scientific value, these math colloquia serve as an important purpose of establishing or strengthening connections between the IMU and the local mathematical communities. So my hope is that all participants will have the opportunity to connect and build new scientific relationships during these days. This afternoon, we are honored to have two distinguished speakers, Wendelin Werner and Tatiana Toro, whose work has influenced profoundly probability theory, geometric analysis, and mathematical physics. So the first speaker today is Professor Wendelin Werner. He's a leading figure in probability theory with fundamental contributions to stochastic processes, conformal field theory, and random geometries. He is currently at the University of Cambridge. He received numerous prestigious awards, including, of course, the Fields Medal in 2006. Wendelin has actively contributed to the IMU in various capacities, including he was a member of the Executive Committee for 2 terms, from 2011 to 2018. So with that, please join me in welcoming Wendelin as he presents Connections via Brownian Loops. So Wendelin, the floor is yours.
In the welcoming address, it was, wasn't mentioned that this is a very typical weather to welcome you here today. This is how it was all these last months. We had this typical weather. I'm sure the Newton Institute program participants can testify for that. So it's, of course, a bit strange for me to stand here in front of you because there are so many different connections with various members of the audience in different directions. I just want to maybe start saying a little word about me and the Newton Institute, because I was here as a postdoc, formerly at the Newton Institute, in one of the very, very early first European postdocs fellowships that were awarded. And in those days, history is what it is. And so military service was compulsory in France, except if you were doing some cooperation with underdeveloped or developing countries. And then if you were doing a postdoc, it could be validated as military service. So the first time I entered here was to knock at the door of Peter Goddard, which was in the office now occupied by Ulrike, with a complete absurd-looking piece of paper that he had to sign for me to indeed be able to validate my military service as being postdoc here, which was basically saying, in case of war between the UK and one of its neighboring countries, you allow Wendelin Werner to take refuge in the French embassy in London. And I felt really embarrassed with that, but of course, Peter showed me I had the first experience of British sense of humor in the way he was raising his eyebrows and just signing, he's saying, oh, these French, or something like that. Yes, and then it was just after, this famous photo that you see over there happened where Wiles, gave the first, proof of Fermat's last theorem, and then we were, it was very exciting to see the blackboard where it happened. Yeah, so anyway, so let me now, I have to start telling you about some maths. So I'll try to do it in a, low-key way to try to tell you a story about one very recent result but maybe with some storytelling about it. And maybe the way to start the story so that you can see where this type of line of thought and research, what the motivation is. Maybe the best is to talk about Isaac Newton, whose picture is just behind there, and the memory I had from when I was at high school. For the first time, I had these wonderful teachers in physics, and we learned about Newton's law. And I raised my hand and I said, yes, thank you very much. This is great. It works, but can you explain how it works? What is traveling between the Earth and the Moon, or the Sun and the Earth? Surely something has to go between them so that they know, some procedure has to be going on so that it works. And basically the answer that I got by asking more and more was that maybe I shouldn't be a physicist, because in some sense the rules of physics are in the end descriptive, right? You describe laws or find ways to formalize what you see, and then you have to accept that and check it with experiments, rather than keeping asking the next question about but how does that and how does it work? And the other thing that you learn is that, well, these type of questions are actually, like fundamental questions in physics, actually, because they are not like so well understood, or at least if you are from a mathematical perspective and, very down-to-earth mathematician, usually the explanation you get are maybe not the ones you were looking for. Like, it's getting very complicated. So the general question is about, how could you make sense of, things, interactions between things at distance, and the type of, every probabilist will go through this type of thought, saying, yeah, okay, then you have to send signals outside to, and the signals come back, and so some interaction has to go back and forth. But if you keep sending signals, at random in all directions, R3, the three-dimensional space being what it is, everything goes to infinity, goes away, and so something dissipates, it doesn't work. And so you try to find some ways, some model that might give you some explanation. Now, we'll come back to that later. I'm not going to explain that, but it's just to of course, to give a little background to some of what things I'm going to say. The other thing is that, indeed, it is true that sort of, the laws of physics are usually, very early on when you follow these classes and you want to become a physicist and you follow these classes, you get these description, and at some point when you're told, that's it, now you have to work with that. Don't ask more questions. And in some sense, this SLE, stochastic linear evolution business that I was involved with 20 years ago, was to, for one particular case, which was this conformal field theories, which was described by some formalism, be able to say, wait a minute, actually, hiding behind the scene, there is a random object that we can, actually describe mathematically, and it's very concrete. It's a random fractal type structures that are around, and the stochastic, these sort of more abstract-looking mathematics is a way to, describe this without knowing that there is actually such an object. So this idea that hidden behind some of these macroscopic laws, you might have some random structures that are very natural, is sort of a constant theme of some of the research going on in probability theory since then. So now, if you are given, now I want to start telling you about this Brownian loops, collection of Brownian loops that we've been working on for some time. So imagine you have a space. So you try to find the simplest possible random, most natural random object that you want to define in space. So structure, sets, or collection of sets. So of course, if it's a random function, this is what is called a field in some sense, and this is, that's what physicists have been doing all the time. Quantum field theory is about defining random objects living in some to each point in space assigns a certain object in the Lie group. But now we go really down to earth and try to define the simplest, possible objects you want. And the idea being you are in a space which is the continuum. So imagine R3, three-dimensional space, but you could also think about something like a grid, but a grid with physical edges, right? So it's called cable graphs, that's how we call them, sort of, like a grid, metallic grid where you can travel continuously on. And then you say, okay, on such an object, what are the natural, random structures you can define? So the first attempt is saying, well, I want to define, I want to choose points at random in space. But then you say, well, I would like to use, the symmetries of space as much as I can. And in particular, I would like, that this random structure is translation invariant in distribution and also scale invariant. That you don't specify a given scale to what you see. And so if you choose at random a collection of points that you choose, according to the Lebesgue measure, somehow the intensity of points, the number of points you have in a given piece of, in 1 square cubic meter will not be scale invariant, because if I blow everything up by a factor 2, I have twice less points, or 8 times less points per square meter. And so you quickly realize that very naturally, the type of random objects you want to define in space, to spread around in space usually at random, would have, they would need to be not points, but, have a size. And at this size, you have smaller objects, larger objects, and you could do that for spheres, you could do that for, choosing uniformly, according to natural scale invariant translation invariant measures, spheres at random in space, independently at random. That's possible, and you can work with that. But as I'll explain to you in a moment, there is one very, very, very special natural way to choose something at random, and that has to do with the fact that what the object you're going to throw in space, or in any geometric structure, are Brownian loops. So Brownian motion, as you know, is sort of this random motion of a particle, completely erratic, and it's not, very difficult to define mathematically. It's not completely trivial either, but it's what you should have in mind is just a random, uniformly chosen curve that you can define. And usually, when you think of Brownian motion, you say, okay, it has a starting point and it goes away. But as soon as you choose a starting point, you're actually choosing points. And I just told you you're not allowed to do that. So in some sense, the really natural way is to say, define closed loops, where the time it's spent to travel loop is not specified. You integrate over it in such a way to make, your measure to be scale invariant. And so you have a very natural measure, which you can define in space, which is this infinite measure on Brownian loops on collection of closed curves. And that has some very special, natural and it's easy to define and very natural property. So it is a scale invariant measure. Therefore, it is an infinite measure because, the mass of measure, loops of size 1 and size 1/2 would be more or less the same. And so you can sort of see that. So once you have such an infinite measure, the natural procedure you have as a probabilist is to say, you say what you do, what we like to call a Poisson point process of such loops, which means that the measure on loops tells you, how likely it is for a given loop to appear, in some sense. So the infinitesimal, likeliness of this loop to appear would be described by this measure mu. And then these loops will appear independently at random. They will, like cracks in space, will appear, completely independently at random at different places. So this is this object that we like to call the Brownian loop soup with Greg Lawler. I think we chose this term right here, maybe during a meeting, I'm not quite sure. But, Of course, physicists will say, yeah, of course, this is gases of loops, and that's a better option. But we had more the two-dimensional picture, so somehow we had it. Yeah. Anyway, so these are just, the picture you should have in mind is that you just, whoops, what do I call it? Sorry. Different loops appear at random, and there's this sort of natural picture. So you could do that in any, everywhere. And so these loops will appear during a certain time. It's like cracks, right, that appear in the wall, and the more you wait, the more cracks you have. And because this measure is, scale invariant, what you have is that, there will be lots of very, very small loops everywhere, right? And, then, big loops here. All right, and there are lots of things you could do with this measure, but I just want to emphasize this one aspect, which is that, as soon as you have a geometric space with something that looks like the Laplacian, some notion of isotropy, okay, you can define that because, knowing the Laplacian is basically the generator of Brownian motion, and then you can define loops, and then you can define this object. So it's not like you're not making any assumption, you just, as soon as I have some space with some notion of isotropy on it, I can define this measure on loops, and I can then have these cracks appearing independently at random in that space. I'm not, doing any choices. Now, what happens is that there is a special time, these cracks appear, and there's a special time if you just stop until that time and you look at the picture you see. So you have this collection of loops. There's a special time where something very special happens. And that very special thing happens is that the collection of loops that you see has what I used to call the rewiring, some sort of a rewiring property of this collection of loops. And it goes as follows. Let me just give you the picture in the discrete case so that you see what happens. Imagine that you see that there was a loop here and a loop here, okay? And you see the union of the loops, but you don't know who was whom. And you ask, okay, I see this figure 8. Was that just one loop? Or two loops? So in some sense, you ask the question, here, at that point, among the three possible connections that you have here, and which one is it? And for that particular choice of intensity of collection of loops, it so happens that this will be chosen uniformly at random, probability 1/3, 1/3, 1/3. For each of the three cases would be the same. But further, if you have now a picture like that, where you have, you see this, you see this union of loops having that picture, and you ask the question, is it now one loop, two loops, three loops? How do they connect? Well, the way it goes is that at each of these points independently, here you choose probability 1/3 here you choose probability 1/3 here, so the choice here does not influence the choice there. You do that choice independently everywhere, and then you have the conditional distribution of the decomposition into loops of your actual picture. Right? So that means that somehow if I look at the union of all these Brownian loops, a very natural object to look at is the clusters, the connected components of the union. And then conditionally on the cluster of loops, the way it's going to be decomposed and split into individual loops is just for each intersection point, you do this choice uniformly at random, who's connected to whom, and then it sort of splits into these individual loops. Now, one way to think about it is to say that these loops, at that precise time when you have these collection of random loops, they become indistinguishable, right? So you don't know who's whom. And so when you have the union of these two loops that overlap, in some sense they communicate, they become only one, which is one cluster. And then you can decide later, that's something you can observe. And now to know who, which particle went exactly where, sort of which loop was whom, that is something you don't see, and you can choose uniformly at random later. And it's not a coincidence that this particular collection of Brownian loops is very closely related to what is called the bosonic free field in the literature in physics, which is basically the zero level of quantum field theory. This is the thing, the most boring things, in quantum field theory is bosonic free field. That's, nothing happens, etc. But there you have this idea, bosonic, particles are distinguishable. It's exactly this type of, concept that is here. Okay. So you have these ideas that these loops, as soon as they intersect, they will create these clusters, and that's, in some sense, a very nice natural structure to look at are these clusters themselves, rather than the collection of loops, because that has its life on its own collection of clusters. The loops, then the way to decompose each cluster into loops is anyway done independently everywhere, and there's no long interaction. Okay. So this says that if you have any geometric structure, so of course not quite, because you want somehow this random walk or Brownian motion to be transient there. So 3 dimensions or 2-dimensional with bounded with a bounded in a bounded domain, or anything on a grid. So it's going to be very important in what's going to follow that. You can imagine I have this sort of grid type picture here, and now the Brownian loops are going to move around here, right? They're constrained to stay on the grid. Some of them will then go around faces like this and so on. But then you can do exactly the same. The clusters will be the clusters, the unions of these. And what happens here in these on these grids is that if I give you a given point, you will have lots of infinitely many, because of the scale invariance, lots of little small Brownian loops that cover that point. But there will be exceptional points here on the grid that are covered by no loop, which are exactly the reason why you will have different clusters when the clusters of loops are not allowed to go through those points. And though basically you take your scissors, you cut your grid at those points that are covered by no point, and then you extract a connected component of loops. Okay. Now, okay, so this is sort of what is now called the critical Brownian loop soup in your space. And it is, maybe I should say one word about some connection with, very natural connection with this thing, with this Gaussian free field, which is this bosonic free field appearing in the literature. And the idea is the following. Imagine that each Brownian motion that travels on this grid, that is easier to explain on the grid, each Brownian loop that travels on this grid is carrying a pack of sand with a tiny infinitesimal hole, leaving the sand behind. And in some sense, when you look at the loop, you see where it went. So this was this thing, the trace that I've seen here. But you could also see how much time did that loop spend at a given point by looking at the, the height of the pile of sand it left behind. Okay. If it spent more time near some point, then the height of time will be higher. So what I'm saying is the occupation time measure has a density which is given by the sand profile left behind it. So this is the story in probability. We like to call it local time. Now, if you take this loop soup, and instead of looking at the connected components, you look for more information, which is the sum of the times spent by all the loops in your loop soup. Right? So the accumulated sand profile left by the union of all the loops then it turns out that this object is just the square of the Gaussian free field on this object here, and it is something which has lots of structures, because so it's a very natural basic object. Okay. So now the story I want to tell you is going as follows. Imagine I'm going to draw pictures in the continuum, but in some sense the result will be on any cable graph first, and then one can try to go to the limit to go in the continuum. So imagine that I'm looking at something, maybe 3 dimensions. I look at the picture on the cable graph like this. And so the way you should imagine, one mental way to try to stimulate imagination is to say, well, these loops, they are created instantaneously, because the space is there, there's space for these things, these random structures to appear. Maybe they are all around you. Now, I have some person is sitting here, some person is sitting there. And then, of course, the question you ask, what happens and how frequent is it that these two happen to be in the same cluster of loops? That they communicate with each other by this chain of loops. That they are actually part of the same particle or cluster of particles. So how often is it going to happen that this one and this one, what's the probability that these 2 points that are far away on my grid actually talk to each other? What's the probability for that to happen? Well, because of the connection with the Gaussian free field that I just told you before, and because Isaac Newton is just there, it just happens that this probability will be just like the Green's function on that graph between these 2 points, which is basically the Newton potential. Okay, so in 3 dimensions, this will be like 1 over r, 1 over the distance between those 2 things. And of course, this has to be some way to describe into resistance of electric networks, or if you prefer, but that's basically the idea. So that's something you can evaluate very nicely. And that's sort of things that have been worked out like 10 years ago by Titus Lupu on cable graphs. And so the idea is 2 points will be in the same cluster with a probability that has to do with Newton's potential. Now, the result I want to describe now, because it's good to describe one concrete result. It's a result that is easy to formulate and state without defining anything. So I feel I have to do it. So that's a 2025 result. So maybe my paper is wrong, and somebody will tell me. But for now, it seems okay. So here's the idea. What is the conditional distribution of the picture of clusters of loops when you condition these 2 points to be in the same cluster? In some sense, seeing that x is connected to y, how does it influence the rest of the world? So what you should have in mind is x being connected to y is going to be via some chain of loops, right? It's going to be some picture like that, typically. And then, okay, you have the other ones, but that's the type of picture you should have in mind. And now the theorem is just saying the following, that the conditional distribution can be described alternatively as follows. First, you choose a absolutely normal collection of loops. Okay, so that are not perturbed by, none of them is perturbed by what's going on, by x and y. And then, okay, I'm going to cheat very slightly, but to this collection of loops, you're going to add a random odd, and that's very important because that makes it very surprising, a random odd number of independent Brownian excursions. So these are just paths that start at X and go to 1. So odd means 1 or 3 or 5, but never even. Excursions that join these 2 points. And the theorem says this picture is the same as that one. So immediately say, wait a minute, there's some problem with even odd there. Something doesn't add up, because you sort of feel, if you're connected by a chain of loops, you have to be connected, the number of parallel connections is going to be even, right? Because each of these loops is going to have two ways, and you sort of feel that something is wrong. And the important thing I should add now is that this theorem is true, but it's true for the union of all these things. I'm not saying that this loop here or this loop here is actually a loop here. You might have been, what you have to do in order to say, that to get the one picture from the other, you have to call your plumber, and that plumber will have to, do some rewiring here and there, in order to create this odd number of connections. But if you try to say, oh, this is a simple bijection, just like this, like that, it's not going to work, because somehow, the number of, rewiring you'll have to do will have to be some very, very complicated, infinite number of rewiring that you have to do in order to find an explicit bijection between that and that. Okay? And so the way it goes is that, what you're going to prove is that not only these two pictures are the same, but also the scent profiles that you see are going to be the same. And that's somehow, that's sort of the statement of this theorem. All right? So in other words, it tells you that, so, the thing you want to extract in terms of information I gave you at the beginning is that you have your 2 points. They live in the three-dimensional space here. And there is, one way to think about it is that you have this matrix, which is this sort of around us, which is this cloud of Brownian loops. You could try to define some dynamical way, how these Brownian loops go, and wonder whether this has anything to do with string theory or whatever, but we want to be down to earth and just say, this is just like Brownian, just simplest object, non-interacting Brownian loops. And then you just say, okay, occasionally X and Y communicate to each other. They don't send out any signal, they're not keeping out, sending signals to the outside world and saying, point Y, where are you? Yes, I'm here, I call you back, and so on. It's just that occasionally they will have this communication channels between these 2 points occurring. And when this channel occurs, and when these 2 points are very far away on the grid, that will typically happen only when you will only typically have only one red path. This random odd number will be 1 if these points are far away from each other. And so when this happens, basically suddenly you have this lightning, this Brownian lightning occurring between your 2 points X and Y. But this lightning, in some sense, modulo this crazy rearrangement because of the indistinguishability property, will not interact with the rest of the world. Because the rest is just a collection of loops that is floating around and is not the pink ones are just not happening, not being there at all. So in some sense, when you have this, collection of, if you can imagine that there might be some dynamic on this collection of loops that go around, then, the intensity of times at which, these points X and Y will communicate with each other will be exactly this Newton potential. And, okay, all right, that's sort of, these things are, these sort of lightnings will appear independently from each other in time, in space, everywhere, without the necessity of having to, send out, messages to the outside world to try to find where things are. Okay. So now maybe I should be more precise, because of course we are mathematicians, and I should say, yesterday I was speaking to to a 6-year-old who just learned about, the overheard discussions about some people claiming wrong statements are true, and asking whether, maybe now is it okay to go to school and to tell your teacher that, and she explicitly said that, right, and say this is true. That's it, And of course, what I said there is not true, right? You have to make a precise statement, so I want to make it, a bit more, give a bit more details now about what the statement says. So the original statement is on the cable graph. So it is on these graphs here. The way you want to do it is going to say, you throw this collection of purple loops on the cable graphs. And now you look at the height at these points x and y. And now you say, you look at the product of the heights at the 2 points x and y. And now you're going to skew this purple collection of loops by saying, the probability of seeing a given configuration will be, multiplied by this factor, this multiplicative product of these two heights, or more or less the square root of the product of the two heights. So you put a slight bias. But once you did that, then this random number of excursion from x to y, the number of those you choose is going to be this Poisson, and following a certain law, depending on this height. The higher it is, the more likely it is that you see that you create a connection between the two. And in that setting, that is correct. You should do it like this. Now, in the limit, when you let the mesh of the lattice go to 0, the big Brownian loops on your cable graph are going to converge to the original Brownian loops here in R3. And these points become very, very, far away from each other. And in that limit, this random number of loops will always be 1. And also, somehow, in some sense, the height at the points x and y will typically be 0 in some sense. So that, there's no reason to skew that anymore, so that in the continuum limit of that model, you have, indeed, this idea that you have this random web of things that is over there, that is the scaling limit of the clusters of these loops on the cluster of loops on the cable graph. And this one has the property that, infinitesimally speaking, the probability that x and y are both at distance epsilon from a cluster, from the same cluster, this will be behaving exactly in a certain way, and conditionally on that, this cluster can be described by just one excursion plus an independent Brownian loop. So, in some sense, this tells you that this matrix, this sort of, these collection of loops that are around, if you are, it's of course the usual trap for mathematicians, right? We understand wide little mathematical structure and this is just a little observation you can make on these collection of loops, and then you say, okay, now I can explain the whole world with my little thing, and that's not the way it goes. On the other hand, you sort of feel that these, collection of loops and their clusters for this critical loop soup in 3 dimensions look like to be, some important structure that you might want to understand better. And so one little remark I want to make is that remember, a Brownian motion in dimension 3 is an object which is, is quite, it's some fractal type object which happens to have dimension 2, fractal dimension 2 in 3-dimensional space. It's not quite a plane, but almost, in particular, it has double points, but no triple points, because two Brownian loop, two objects of dimension 2 in 3 space will intersect typically. But if you are not quite of dimension 2, you take 3 of them independently, you lose a dimension 1 at each step, they will not intersect. So these Brownian loops will have double points, but no triple points. So particularly two Brownian loops will indeed intersect in 3 space. And so you can try to look at their clusters. And then what you see is that, how big is going, the cluster of loop is going to be much bigger than a Brownian loop. That comes out just out of the self-similarity and scaling variance of the measure, because if you see one Brownian loop here, in each piece there will be a positive probability to see another one that intersects it. And here again, you can continue, and therefore, you have this additional fractal structure on top of a Brownian loops as a fractal tree of different loops. So it's easy to see that these clusters of loops will have a dimension which is bigger than the Brownian loops themselves. And it's very easy to guess what the dimension is going to be, because I just told you the probability, that here of x connected to y decays like in 3 dimensions, like 1 over the distance. And so how do you, one way to realize it, say, well, x has to be in a very big cluster that goes all the way to that distance. Y has to be in a big cluster like that. And then, the probability that they are actually intersecting is going to be, that they're actually in the same will be, positive once they both make it far away. And so you sort of see that this will, there will be a 1/2 here coming up, because this is 1/2 squared. This has to happen here, this has to happen there. So the probability that x is at distance epsilon from a big cluster of size 1 will be typically decaying like square root of epsilon, which tells you that the dimension of this cluster of loops is going to be 5/2, 2.5. So this magic, connection, these magic clusters that are behind the scene in these, creating these things are objects you can describe, you can say things about them, and you sort of can get all the way to say, yeah, their dimension would have to be necessarily 5/2. And maybe I should conclude with just one additional comment, is I insisted on dimension 3 because we are in the Isaac Newton Institute, but this works in any dimension, and depending on what dimension you play this game in, the answer is going to be very, very different and give rise to very different phenomenological, descriptions. So in particular, so this is like, my conjectures of mine that I wrote down at some point, which hope not going to be conjectures for much longer, but where basically, if you imagine that you do this in dimension 5. So in dimension 5, what happens is, in fact, look at 2 Brownian loops. They don't intersect because they are dimension 2, each of them. So it looks like there are no clusters of loops because the loops don't intersect each other. On the other hand, if you do this on the cable graph, as I told you, there's still, it's a locally one-dimensional structure, so you will have this picture that these, 2 points can be in the same cluster of loops on the cable graph, and that this will decay like the potential in dimension 5, which goes down like 1 over the distance to power d minus 2, which is 3 in that case. So how could that be? That here, in the limit of the cable graph loops, you have connections, and it looks like you have a fractal object with dimension, 3.5, these clusters. And here, in terms of the loops, nothing happens. Well, what happens is that you have an overlay. The way these loops, these clusters of loops are going to be created, has an overlay of 2, complementary phenomena. And of course, again, that rings bells, going back to some things that, I never understood this part of the physics lectures, and now I get something that sounds a bit like it. It's not explaining anything. But the overlay is the following. You have the macroscopic loops. But on the cable graph, you also have the very small loops that could create big clusters of small stuff, even though each individual loop has disappeared in the scaling limit. It's not a macroscopic Brownian loop. So the idea is that you have these 2 complementary things. The loops are there, and then you do some infinitesimal percolation in the, you have the infinitesimal loops that play the role of, like infinitesimal glue that you spread uniformly, in some sense, in your 5-dimensional space. And you just put enough glue so that you can you can connect loops with each other and then create clusters of loops. So some of the clusters of loops will be coming from the combination of the macroscopic loops and some microscopic information coming from the, from the infinitesimal loops. So you can zoom in, you can get more and more information about the small loops, but the microscopic ones, they are always random. You'll never see them if you just observe the macroscopic structures, the macroscopic loops. You will never see them, but they are there to tell you, what is actually going on. So you have this sort of phenomenon which is very typical, intrinsically continuum random stories. This is not something you can explain by discrete, by saying, Brownian motion is like random walk, or, percolation continuum is the same as the scaling limit of discrete model. It's something intrinsically continuous. And here, this is already the case for this thing here. You need to be on this cable graph connections in order to make this work, where you start having, weird, random phenomenon going on. And that's fun to think about as a mathematician, because when you have nice random objects, they are also related to other parts of maths, and you can start playing around as you want. All right. Okay, so I hope I entertained you a little bit. I hope to wish all the best to the executive committee. I know how daunting it is when you receive in your mailbox, how is it called? The plan of, 0.52, 0.3, and 52.4, and you read all these things, have to do that for the good of the community. So anyway, so thank you very much for doing that job for us. And I'll stop here. My talk. Thank you.
I think we have a few minutes for our questions. Would you like to take the opportunity to ask?
There's one there.
I guess this relation to position function for Gaussian random fields and so on, this is for the two-dimensional case, right?
I'm sorry?
The relation to the Gaussian random field, the Gaussian free fields.
No, it's in any dimension. It works in any dimension. So basically, this is sort of a, it's one of these stories, basically, the way it happened historically, it's quite interesting because, in some sense, this result here on the cable graph is it's something, you take any finite graph with physical edges and you have this identity with even odd. And that had escaped us for up to now somehow, the simple identity, this sort of what we call switching identity. It's not a difficult result. It's just, we missed it, right? Once you know it's true, you can find 3 or 4 different proofs, and the way it worked is very similar to what happened, maybe historically I should explain to you that, the way it worked was that the SLE showed up, right? You have this random object. One of these SLEs happens to represent the scaling limit of loop-erased Brownian motion. And as its name says, loop-erased Brownian motion is a Brownian motion where you erase the loops. And so here are the loops. And so we had this paper with Greg Lawler where we said the collection of loops that I erased by doing a loop-erased Brownian motion are just the collection of loops in the loop soup that are intersected by the loop erasure. So, you can first define the loop erasure and glue the loops back on by collecting all the loops in your loop soup that you find. That's how we, define the Brownian loops. Then, that was starting in 2 dimensions, but then it was already clear this part works also in any graph. But then came, all these wonderful papers by Jason Miller, Scott Sheffield, Odette Schramm, of course, initially, that were relating the 2-dimensional Gaussian free field with level SLE pictures and level lines of the Gaussian free field to view the Gaussian free field in 2 dimensions, the continuum Gaussian free field, which is a very complicated object, and to relate it to these SLEs, which are also quite elaborate objects in 2 dimensions. I'm just saying all this in order so that you see that, how it's sort of instructive to see that, then you retro-engineer and then you say, oh, actually everything can be explained, in all generality. It works not only dimension 2. And then sort of we realized, so that's the paper with Sheffield, that you can take these clusters of Brownian loops, you take their outer boundaries, you get these SLEs, and these level lines could be realized as, somehow the level lines of these sand piles, if you want, in the two-dimensional pictures. So there were a number of people involved there, and then Lejean, Yves Lejean, who was basically in the office opposite to mine in Orsay, basically then he said, oh, wait a minute, actually what you're saying, the relation between the loop soup and the Gaussian free field, this works on any graph. Take any discrete graph, you take, properly defined random walk loops, their sand pile is going to be this square of the Gaussian free field. And then Lupe, who was a student of Lejean, said, if I add the edges, then I'm in the one-dimensional world. These sand piles are continuous functions. I can look for their zeros, I can look for their clusters, and therefore there, this connection will work much nicer. And the probability to be in the same cluster, right, being connected, if they are not connected, the Gaussian free field will choose a point, a sign independently at random, depending on which cluster they are. And right, so then sort of you could retro-engineer this idea that you have the relation between loop soups and Gaussian free field works in any dimensions. And now in the two-dimensional world, so that's going to give me the occasion to write a few names on the blackboard. There were like, a few people which were, on the trail of this identity. So in the two-dimensional case, so we have this paper with Wei, Jian, and also another former student of mine, Mathis Lindkühler, who was a Part 3 student here in Cambridge before coming to Zürich to do his PhD. And there are also Elie Heidecon, who's a French, very clever French mathematician now working in Shanghai, and then a paper by Lupu, Gigot, and Kian, where some version of these type of things were appearing, this sort of strange, even odd symmetry breaking story, were appearing in some way in the continuum two-dimensional world. So not at all about cable graphs. There was something very strange going on. So we had this sort of a result with Wei and Mathis, where he said, I look at this picture here in 2 dimensions, I can find a point here somewhere on the cluster, which has a probability exactly 1/2 to be in a loop, or not in a loop. Because, many points on this closure of this cluster, might be points that are only reached by an infinite chain of loops, so they are no loop themselves. So we could sort of see that there's this strange thing going on, that there's a parity issue, mysterious parity issue coming up in the 2-dimensional case in the continuum. And then exactly as Lejean did, then suddenly you realize, wait a minute, actually this is just a symptom of something very elementary going on in any graph, on any cable graph, this even odd switching result. So it is not 2 dimensions. In some sense, the philosophy, I mean, this is what my, when the sort of cycle of this SLE stuff, was maybe coming not to an end, but getting less, the natural question always is saying, okay, in 2 dimensions we understand pretty well these random fractal structures, they're all related to an SLE. Okay, what can we do in other dimensions? And it's clear that in this whole picture, the one object, which happens to be central, because here, in the end, in the paper with Scott, we showed that any SLE could be represented as boundaries of clusters of loops. The time it rains is just a parameter you have to let your SLE kappa vary here. So these clusters of loops, they are there in 2 dimensions, and you construct the 2-dimensional stuff out of it, but they exist in any dimensions. And the Gaussian free field exists in any dimension, and you can relate them in any dimensions. And yeah. And again, of course, maybe I should add one thing is that, one dimension that I didn't mention is, you sort of see it's very critical, it's dimension 4, because then the Brownian loops almost intersect, but not quite. So there's something special supposed to go on as well. And as you know, I mean, 4-dimension field theory is an important question. I think one lesson, I mean, sort of one personal, lesson I learned is that sort of, if you look back at the history of, probabilists trying to construct something that might explain, some of the physics going on, it's just, there's just a lack of tools, right? So in the 60s, people said, oh, we can define Gaussian processes by just defining covariance function, and that's it. And then I said, okay, now let's try to explain the world with Gaussian processes, and oh, no, it doesn't work, okay? And then, so if you want to define infinite collection of things that interact with each other, well, you don't know how to start, you don't know how to define them, so you can't say anything. And so as soon as you have a little, lead that says, oh, here's something that I can try to, define, you might, want to go into that direction. I should emphasize that, also these gases of Brownian loops, there's a way to reread somehow, all the things having to do with Bose-Einstein condensation type, questions by saying, these are gases of these Brownian loops, but now they start interacting. You sort of penalize, they don't like intersecting, and then you start putting some weight on them. That's one aspect. And yeah, okay, maybe I should. It is connected to lots of other things. So you probably heard that on the stochastic PDEs directions, there's a lot of activity around following the structures by around people. I mean Higher but many other people doing looking at the evolution of this 5-4-3 model. The so-called 5-4-3 model is the model in 3 dimensions that heuristically can be viewed as take a collection of Brownian loops, independent, but then they are interacting, and you penalize the probability configuration by something that is counting how many double points you have. Right? The number of those points here, and you put e to the minus this number of points in front of your probability measure, and that's the thing you want to call the 5-4 model. Right? Phi squared is the number of points, and the square is the number of double points. And of course, the whole difficulty is then it's not absolutely continuous with respect to the field that you started with, so you don't know how to define this. But there's a whole idea, how to define these collection of interacting loops via some natural dynamics going on the spaces on these collection of fields. So there's also some story there. So I guess after having given, there was one tiny question and I gave a 10-minute answer, so now nobody will dare ask me a second question, so never knows.
Yeah, I'm afraid there's no time left, so let's give a round of applause to our speakers.
Mathematical Sciences Institute, former MSRI. She's a member of the IMU Executive Committee and in fact one of the 2 vice presidents. And her mathematical contributions belong to the interface of PDEs, harmonic analysis, and geometric measure theory. She received several international prizes and awards, Sloan Fellowship, Guggenheim, Simons Foundation Fellowship, and she also was invited session speaker at the ICM 2010 at Hyderabad in India, right? So with that, please join me in welcoming Tatiana as she presents Geometry of Measures.
Thank you. Thank you, Paolo. Thank you for the invitation to talk here. It's a pleasure. It's actually the first time I'm an official visitor to the Newton Institute, even though I lived across the street for 6 months when I visited UCL and my family was here. So it has been a pleasure trying to find out the nursery, the school, and where we lived years ago. Okay, so my talk is going to be, I'm going to tell you a story. So let me tell you the different pieces. The goal, in many ways, of geometric measure theory was how to characterize smoothness in non-smooth world. I give you pictures so you get an idea. I'll talk a little bit about the history, and I'm going to talk about the round world and not the round world. And it's interesting because one of the first things you learn when you do a class in, analysis is that in Euclidean space, all metrics are the same. All norms are the same, you know, just some balls look round and some balls look a little bit different, but they tell you everything is the same. So maybe it's true, but I just am unable to prove it. So that's one of the things we're going to talk about. But first, so how to characterize regularity in a non-smooth world? I want you to look at pictures. And if I ask you, well, how do you, you might have ideas of what's smooth and what's not smooth. I mean, you're going to tell me, Tatiana, nothing's smooth because even the smooth things have intersections. So that's the sort of things we want to talk about. Okay? And you might say you like some better than the others. This is a value judgment. We're not going to talk about that. Okay, so let me start by the origins of geometric measure theory, at least my biased interpretation of them. I can say there's two, and I'm going to say there's two because I come from two different schools. So the first thing you can say is the plateau problem. What's the question? You have a wire that expands to start with that is the boundary of something, and you're interested in finding the minimal surface thing. And then, of course, you will love to know that this minimal surface thing you wanted to say is smooth. But even though it's not exactly the same, you see you have a wire here on the left, and you put it in soap, you took it out. Soap is not minimal, it's constant curvature. But you see, whatever that thing is, it's not smooth. I mean, yes, it's very smooth, and then you have intersection. So if you wanted to talk about what minimizes, what accomplishes the plateau problem, you needed a larger class of things. Okay, now let me go to, and I teach, when I teach has been a while, I have not been in the classroom for a few years, but when I teach measure theory, I often remind the students that there was no internet, and that there was no archive, and that therefore, when Lebesgue and Hausdorff were doing things similarly, they actually, and Besikovic and Hausdorff, they actually didn't know of each other's existence, so that's why things are strange. But remind you, a very classical result. If you have a set of positive measures in the real line, almost every point has density 1, which is that statement there. So what Besikovic asked between, in the 20s and 30s, last century, if you have a set, he called it of linear length, positive and finite. Hausdorff called it of Hausdorff measure 1, positive and finite. So something that, think of a curve in R2, that's kind of dimension 1, although I'm lying, but it doesn't matter. I think Wendelin lied a little bit here, so I promise my lies won't be worse than his. Okay, but what he has is, I have points of density 1. I have a set, and I have a lot of points of density 1. What can I say about this set? And he was able to show that this is a countable union of C1 curves up to a set of measure 0. Okay. So that's a smooth set for me. A set that is a union of C1 curves up to a set of measure 0 is a smooth set. And so what happens in higher dimensions? So now you have, and again, the Hausdorff measure is just a generalization of Lebesgue measure just in higher dimension. What happens if you have a set of n-dimensional Hausdorff measure that's positive and finite, and you have that this ratio here, this density, is 1 almost everywhere? What do you know about it? It's fair, it's roughly the same thing. What happens if we replace Hausdorff measure with other measures? Okay, and then what happens, and you see, I didn't tell you that these balls were round, and you all imagined them round, correct? Talking of bias. Well, the L4 ball feels really bad, but these are round balls. What happens if now we think of the L4 ball or any other ball? You're square. A square is a ball. What can you say? Okay, so those are the questions that motivate this talk. Of course, there's lots of work, so I'm going to tell you the history of the work. Then I will tell you why I asked the last question. I'll tell you how COVID plays a role. And then Now, we're going to live in the round world for the next two sections. So, balls around. So the point is, how does the infinitesimal behavior of a measure determines the support? So you're going to take a measure. It's a locally finite measure in RM. I'm going to assume all of you took an analysis class at some point in your life, and you remember more or less what a measure is. And if not, think of English. That's what measuring something is. You have a measure. You look at this density ratio. And you look at what happens as R goes to 0. Of course, if your M is N, you're in Rn, that gives you a 1. You know, this ratio is constant. But in general, you look at this limit, and if the limit exists and is positive and finite, you say that the N density of the measure exists. And so the question is, well, let's imagine that you have a measure, locally finite measure in Rm, and this density exists almost everywhere. What can you say about the measure theoretic support of mu? Forget if you, the measure theoretic, I write that there because I remember giving a talk and I said, what can you say about the support? And I had somebody say, you mean measure theoretic, so I'm not gonna do that lie. But what can you say about where sigma live? Where mu live? What is there a structure to this set? Okay. And then what happens if this is a special type of measure, which is the Hausdorff measure restricted to a specific set? Then do you have more information? And don't hesitate to stop me. Okay. So what can I expect? You know, I'm not going to show up here and tell you, oh yes, and the sets are smooth, because I will be lying, and that would be a big lie. So remember, I told you what my notion of smoothness are. So I'm introducing a smoothness for you. A set is n-rectifiable if A is included an accountable union of C1 n-dimensional submanifolds and a set of Hn measure 0. So a set that I don't see. And I say a measure is n-rectifiable if it's absolutely continuous with respect to Hn, which means if the set has Hn measure 0, mu has measure 0, and then there exists a countable union of C1 submanifolds where the measure lives. Okay, and that's smooth. So for the second, just so that, you know, so for me, smooth is if you change countable directions segments, you put them all together, that's a smooth set, okay? That's a beautiful rectifiable set. But many things, you imagine, so the 3 spheres that you saw initially, they're of course rectifiable. The picture of where the wire, that was rectifiable. The other beautiful looking pictures are not rectifiable, okay? But we're gonna talk about that. Okay, so notion of smoothness, forget the set of measure 0, countable union of smooth manifolds. Okay, that's the most I can expect. Okay, so first big thing, so if you come from geometric measure theory, you realize that geometric measure theory might be the only field whose name was given by the title of a book. Federer called his book Geometric Measure Theory, and one of his results is that if the set is n-rectifiable, the density exists almost everywhere. So the question is, what happens in the other direction? And there's lots of things that happens. So this little table shows that things are different if you know mu is Hn restricted to a set versus if you have a local measure. And so I put the dates because Besikovich is 38. You see, Besikovich was 1 dimensions in R2. Then for the general measure, they were able to do the same thing a few years later. Then the big thing in 1950, you were able to put higher codimension. And then they were on the, oh, and there's, sorry, there must be a light here. Is there? No. Uh-oh. No. For the Hausdorff measure, there were a few results, but it really took until 1987 for Price to prove the full result. And this was honestly a masterpiece in geometric measure theory. And when you look at his proof and you ask him, so actually, the anecdote is when I spent time living in Cambridge but working at UCL, I came to visit David Price. And one of the things I wanted to do is, I had used his work, but I wanted to understand his motivation. How did he think of doing this? So his answer was, oh, I had some friends in Israel who were doing statistical mechanics, and I decided to look at the sort of things they were doing, because everything was about moments and a number of things. And then we got to a point, this very important lemma there. It's like many times in analysis, there's a changing limits, it's kind of, and then I asked, how do you think that is? Well, that one I never understood that result very well, but it works. And so, but basically, Price, it's really a masterpiece, and there's lots of things in that paper. But it took some time, and actually already there he asked, what happens if your balls are not round? Okay, so what were the ideas in Price? The ideas in Price is, if you're trying to understand how smooth a function is, you try to look at the tangent. So what he did is he looked at tangent measures. What's a tangent measure? Your set's here, your measure lives on these, you blow up, you start enlarging, you see what happens. He looked at those measures. He looked, and then he found out that when you blow up, almost all tangent measures are n-uniform. And what's n-uniform is what you see there, is the last definition. The measure of every single ball on the support is the same. It's exactly r to the n. Okay? I'm going to ask you, so if you get lost during the talk, or, just think of how many measures even that have this property. And even, I'm going to give you a simpler question. Let's imagine for a second that you're in R3. How many measures do you know that have the following property? You live in R3 and you're looking at a measure that every time you take a point on the support of the measure and a radius less than 1, the measure of that ball is pi r squared, or put r squared. Okay? So if you get bored, don't worry, at the end I'll ask you if you have the answer, and if you've taken Calculus 3, you're able to answer this question, which means all of you know how to answer this question. Okay? I won't put anybody on the spot, but I won't call in. Okay, but so what Price was able to do is, okay, I blow up, and here is what my tangents are. When you're teaching calculus, at least, and now I have some questions about how we teach calculus, I'm not going to say that, but what you tell the students, if you blew a blow up and you have the graph of a function and it gives you a line, there's a fair chance that that graph is nice. Okay, so being able to understand the tangents are nice, and then the second key idea is in that little sentence you see how I say, well, if all your tangents are uniform, then basically all your tangents are flat. That's a huge piece of work. Okay, that's where all the things from statistical mechanics came. But what I want you to take away is that understanding the tangents is important. Okay, questions? Okay, so now I'm going to change for the second topic. Well, not exactly. There's two big flavors of geometric measure theory. There's the geometric measure theory that I have presented, and that is what I will call the quantitative geometric measure theory. I'm not going to talk about that. That one relates a lot to harmonic analysis. And the questions, rather than having qualitative statement, your accountable union of C1 pieces, you want to say each ball is 10% a C1 piece. Okay? And that relates, again, as I said, to harmonic analysis and therefore to operators. And so there's also a question, which is, if I understand, if I look at principal values, I'll remind you which is this thing on the bottom. So you have a kernel. And let's take this kernel. The kernel y minus x is y minus x over y minus x to the n plus 1. If you come to PDE, you know why I'm taking this one. I'll mention that just at the end. But you look at this and you look at this quantity here, the limit as epsilon goes to 0, where you take away the little ball. These guys, of course, blow up at 0. So you take away that, you look at this limit, and this thing exists. And you ask, if I know that this thing exists with respect to the measure, do I know anything about the measure? Okay? And this comes from looking at the Hilbert transform. This comes from quantitative geometric measure theory. This comes from many different places. But that's the question I would like to ask. You know, if you're in R and a large ball, and you look at the integral of 1 over x, and you look at the principal value, you realize it exists. Of course, the thing blows up, but when you look at this limit, it exists. Okay, so assume that you have a locally finite measure in Rm, that this thing exists. Same two questions. Can you say anything about the support of mu? And can you say anything if mu is Hn restricted to sigma? So here the answers are a little bit different. Matila and Price prove that mu is, I should say, n-rectifiable, sorry, if and only if the principal value for this specific kernel, which is the risk kernel, exists, and if the lower density exists. And so this thing is the lower density. Why do I need that? To make sure that I see enough, otherwise I don't see enough. Okay. So that was one result in the literature from 95. And then there was another result from Tolsa. You're going to say, but you know, it's included in the previous one. Yes, it is included in the previous one. It's an if and only if. But this one doesn't have the lower density. This one uses techniques from the quantitative world. And I just wanted to mention because these two worlds for a long time lived completely separate and only now are coming together, and that has been very fruitful. But I'm going to forget Tolsa. I'm going to go back to how did Matila and Price did that. You're going to say she's repeating her slides, she's cheating, she did it easy, but, well, kind of. So they do the tangents, and I have to say, you know, as you work in a field, you have techniques that you like better than others, and so I always blow up. My first reaction to any problem is I need to blow up. So they did blow up, and when they blow up, they show that all the tangent measures, all always means almost all, are symmetric, and that's what it means to be symmetric. And again, there's another typo that should be a nu, excuse me. So there's the integral. So a symmetric measure is, you know, the center of mass is always 0. No matter what ball you integrate, the center of mass is always the center of the ball. And now the question is, with lots of work, they show that that means that almost all tangents are flat. Okay. So just to say, having tangents is important, and understanding them is important. So now those are the takeaways. So on the other hand, the rectifiability has to do with being a countable union of C1 pieces, okay? I told you, and we all said, you know, somehow is not very different. I mean, in fact, it's Lipschitz pieces, and these notions don't depend on the norm that we're using. So why does everything, well, not why does everything depend on round balls, but can we change the round balls to something else? And I often use the L4 ball. And so that was one of the things we wanted to address. So let's go. Now we're going to look at measures and density in other norm spaces. And so, so this is a question that has been around for a long time. Here is your norm. I'm going to give you two examples of balls. The first ones are these ellipses. Not, you know, so that's the distance you have, and the LP ones. So let me remind you, this is what the LP balls look like. And so after Price's work, there was already a lot of work of, okay, can you do it for somebody else? And of course, the initial interest was in L1 or L infinity, because everybody thought that, for example, Manpur L8 1 was going to be too easy because it's also uniformly convex, and therefore it should be easy. And so let me tell you what's known. So Laurent proved that there was a mass. So an important result in geometric measure theory in this area, which I did not mention before, is you might ask, what happens if that n, you know, I always put an integer when I compute the density. What happens if I put 3/4? What happens if I put s? And so there's a real theorem of Marstrand's that tells you, no, if you have a measure and the density exists almost everywhere, that density has to be with respect to with an integer, okay? So in this space, when you choose a ball that is not round, you're seeing all the results here, okay? So the results are, there's a Marstrand type result. So if you have the density exists with respect to the L infinity or the L1 balls, and you are in R, you know, and S is between 0 and 2, then you know that S is either 1 or S is 2, and that's it. And then my colleague Bobby Wilson showed that if this norm is uniformly convex and is the Hausdorff measure restricted to a set, and the density exists, then mu is n rectifiable, and that's it. Okay, so I said that this question was drawn with Bate and Wilson. So COVID started. Wilson had been visiting David Bate in Warwick, and I had been talking to David Bobby about Wilson about this problem. And so in some sense, I like this problem because it carried us through the pandemic. The thing we had to look forward was our very long Thursday meetings where we talk about this problem. So, and we've met for about a year and a half, and you'll see, I'm not going to show you any results on this problem. I'm going to tell you this classic thing, okay, you work, you don't get anywhere, and then you get another problem, and then you formulate a different problem to try to understand this problem, and then you get some results. But I thank my two collaborators because that's one of the things that kept my sanity, that and long walks during the pandemic. Okay, but so our question was, we wanted to understand, let's imagine LP, okay, more general, uniform, so in general we look at uniformly convex, but LP balls. And we know that I have a measure, and the density exists almost everywhere with respect to LP balls. What can I say? Well, I understand very well that the tangents are n uniform. Remember, you're doing that homework over there of who can be n uniform. And now the problem is that I cannot classify. There's a classification for the n uniform measures with respect to round balls, and we don't have the same thing. Okay, and I reminded, maybe I'll ask a question to the people in statistical mechanics afterwards. And so they are really in the case where P is even, I know that the support of an L2Q uniform measured is a real analytic variety. This is not our idea, it's just an implementation of the idea of a Kerr-Hyman price. So, but that's not good enough to give us any information. Okay, so we were frustrated because, as I said, we met for at least 4 hours every Thursday. We did homework for it. We got nowhere. So we decided, okay, so, and you agree, round ball, L4 ball, they're really nice and round. So we decided to change the problem. Let's imagine that we look at densities with respect to ellipses, and ellipses that can change direction and an eccentricity in each point, but each of them is, none of them collapses. And let's imagine we look at densities with respect to these. Do we have any results? And what we were trying to understand was still the LP case. And you're gonna, because although the balls in LP are round enough, kind of fluffy enough, there's a linear structure in this problem that is not there. So we were trying to understand what makes things work. So we look at this problem. Let's imagine this. So the B lambda A R is really an ellipse where you have twisted and the eccentricity depends on lambda R. And you look at this and you ask, well, if this density exists almost everywhere, what can you say? And it's that mu is n rectifiable. Okay? And so we were very pleased because, well, okay, it worked. In fact, there are two proofs to these. One that is very simple and just pure measure theory, and one that's very complicated, if you especially don't know the technology, but talk about the tangents. And so we were able to also look at the tangents, and we understood the lambda tangents. But you didn't need to invent the lambda tangents to answer this question. So we left it there, and then we would like to look at the same problem with respect to the principal values on other norm spaces. So one of the things I think in Paolo's introduction, he mentioned I do PDEs. So I am always, and you won't see a single PDE now, but for those of you who are in the area, you might recall that the Riesz transform in codimension 1, the Riesz transform is the gradient of the fundamental solution of the Laplacian. Wendelin mentioned it. He said in R3 you have 1 over x to the 1. When you take the derivative of that, that gives you x over x3. I mean, so we're talking about, and so that's where this comes from. So let mu be, and so now this is joint work with my current student, Emily Casing, who's graduating, my former student, Max Gehring, and my colleague, Bobby Wilson. And we look at a finite measure. We look at the lower density being positive and finite. And we have this lambda, which is a matrix value function, which is measurable. And then the following are the equivalent. The measured is n-rectifiable. And for almost every x, this principal value exists. And if I were you, so what would I like to, well, if I were you, the first thing I will ask is, you write that lambda, why do you put a lambda minus 1? This looks like the weirdest thing on earth. So I'm not going to explain in detail, but again, if your m is n plus 1, and you were looking at a divergence form operator, so divergence ax gradient of u equals to 0, and you're looking for the fundamental solution of that operator, and you look at its gradient, it looks exactly like that, where that I said that A is lambda squared. Okay, so bear with me, this is the gradient of the fundamental solution of an operator. And so that was a motivation. So what would I like to kind of emphasize here? That is very similar to before, except before we have lambda was the identity. For a minute, lambda is the identity, this is the thing I had shown you before. Now, why do I like this one? Because here I put lambda, and I have, my balls are with respect to the right metric, okay? So notice I am not removing a round ball. I am removing the ball that comes. I am removing the dual of the ellipse that I show you. Okay. Okay. Questions? Okay, and I should always show a proof, so we're gonna talk a tiny bit about this proof. Don't worry, it's not gonna be complicated. So there's two directions. So the first one is, let's assume that these principal value exist. We do a blow-up procedure, and we prove that all the lambda tangents, so when you do, when your students look to see if the graph of a function has a tangent, they blow up the same way in every direction, okay? So when you do with a lambda tangent is that you favor some directions in one way and, different directions differently, but you never break it, so it's not like you suddenly go crazy this way, you go a little bit more this way than that way, but that's what a lambda tangent is. And you show that all the lambda tangents are symmetric. That will allow you to show that almost all the lambda tangents are flat. And if the lambda tangents are flat, then you can show that all the tangents are flat. And roughly every time you know that the tangents are flat and you have a density statement, you know how to prove that something is rectifiable. Okay? So that's how this direction goes. And the other direction is a little bit interesting because it goes to, so if you're rectifiable, you need to show that this limit exists. So if you're rectifiable, you're able to prove that these two principal values are the same. And then you're able to say that if the two principal values, the two principal values are the same, and therefore the second one exists. Okay? So to go from the first bullet, you need a fair amount of harmonic analysis. It had been announced by Pugliatti, but we present a different proof. And then the second one is just an interesting change of shape, which amounts to, I said you dilate in different directions, you just make that clear. Okay. Looks to me like I went way faster than I had expected, so I would like to, I'll end by, first I always introduce my collaborators, so David Bate, Max Gehring, Bobby Wilson, and Emily Casey. And I want to finish by actually, so the problem we wanted to look was what happens with a measure as densities for LP balls. The truth is we still don't know. It's very interesting because if you ask an expert, every expert tells you, oh, of course it's true, because if it's true for round balls, it's true for the other balls. On the other hand, even David Price believes it's true, he still doesn't know exactly how to do it. The reality is now we have a new idea, It's a little bit too early. It was something that we didn't notice, but is very interesting. All of these for strictly uniformly norms. Remind you, uniformly convex norms, which is the same as strictly convex in finite dimension. Remind you what that means. That means that if you have a ball and you take 2 points on the unit's ball, the middle point lives inside. Seems like a detail, but it's important, which means we have no idea how to do it for L1 or L infinity. Okay, and those will be very challenges. But we still are stuck. So, I mean, I know there might not be that too many grad students here, but I always like to tell the grad students that positive things come out of being stuck for a while. It's thank you so much.
Would anybody like to ask a question to our speaker?
Does this tell anything new about harmonic measure if you apply these things to harmonic measure?
Well, one of the things that I didn't say, it tells you that, so it tells you something about elliptic measure in some sense. So it tells you in the following twisted way. If you have a divergence form operator, yes and no. If you have a divergence form operator whose coefficient are, I'm going to say Holder continuous, that's more than I need, okay? Then, and I look at the corresponding risk potential, so derivative of the fundamental solution, you can characterize rectifiability by the behavior of that operator, yeah, with existence of principal values. So you see, I chose something here. I say if these exist, but I didn't relate it. I said it relates to the operator. To make sure that it works for the solution of the operator, you need to assume that the matrix is Holder continuous. So in that, in that twisted way, it tells you something.
I wanted to ask you if you could comment a little bit about the possibility of having this type of results on curved spaces rather than Euclidean spaces. Would it make any difference? And infinite dimensional also spaces.
No. No, I don't know about, so, I mean, there's lots of geometric measure theory now on infinite dimensional spaces, but no, not these. Here, so, and I haven't asked you, remember that I have a little bit of time, so I'm going to ask you the answer to your the question I asked. But the techniques of, it might be that if you ask me in a year, I'll give you a very different answer. So it's an idea of David Bate, who is looking at characterizing rectifiability in metric spaces. So, yeah, that might allow us to look at this problem in the LP spaces from a different point of view. Okay, but so, in infinite dimensional, even, what's infinite dimensional? What's the notion of rectifiability? If you have, you can say yes, and finite dimensional plane, but that's not quite correct. So is these new ideas of David Bate that tell you? But we're far from being able to say anything. And the linear structure appears to be important to some extent, although it shouldn't. So did anybody get the answer to the question? What's the sphere, you're in R3, and I'm going to do the reason I'm going to give you an answer, I'm going to be able to give you a bigger answer. You're in R3, and you have a space, so you have a measure that for every radius less than 1, you stand on the set, and you look at the measure of the ball of radius R in R3, and it gives you R squared, or the constant times R squared. And you actually know two, all of you. You know, of course, any two plane, but that one is cheating. But if you take the sphere, the two sphere, and you place yourself anywhere, and you look at the extrinsic ball, it's R squared. And why did I take the time to do that? Because one of the things that allowed Price and allows all of us to show that if you have an n-uniform measure or a symmetric measure that is then almost all tangent measures are flat, is the following theorem, a theorem that says one of these measures, either symmetric or n-uniform, is either flat at infinity or is very non-flat. And so what does this have to do with a sphere? What this allowed Price to do is when you look in Rn and you look at measures of codimension 1, which are in R4, a 3 uniform measure, what he was able to say, so if you're in R2 and you have a 1 uniform measure, is the Lebesgue measure on a line. If you are in R3 and you have a 2 uniform measure, is the Lebesgue measure on a plane. And if you're in an R4, then you actually have two options. Either you're flat and then you're a plane, or you're very far from flat. I'm sorry, I cannot move this arm too much, but it's something like this, and is the cone, is the light cone. And the way he created this example was by putting a lot of these spheres together and creating these. And actually, there's a full classification in codimension 2 of these measures by one of my students. And again, it's a combinatorial approach to putting S2 spheres. So this S2 is the basic example to construct all the ones that we know. Any other questions?
Any other question? Okay, then let's give a round of applause to our speaker.